just a little bit about our project. Our project is the Building CS project, funded by the Martinson Family Foundation. It's run out of TCNJ's Center for STEM. The goals of this project are to increase computer science education opportunities in New Jersey, as well as provide support for new and existing computer science teachers. So we have individuals on our team working with legislators and school boards throughout the state, and we have a series of free professional development opportunities and are starting a new mentoring program to work with teachers and help them get the resources they need. Some of our opportunities that we have offered in the past and will be offering again this fall: programming with Arduinos, Python Unleashed, fundamentals of Java, Mindstorm workshops, as well as just some basics on teaching intro to computer science. I've provided our website where you can go and look for any of these professional development opportunities, as well as my email address should you have any questions regarding our program. Before I hand over the reins to Richard, I'd just like to go through a few little logistical issues with the software. Under webinar materials, you should see, under handouts, you should see anything that Richard has prepared to share with you. You can feel free to download them. I just will point out that they need to be downloaded before the conclusion of the webinar, because once the webinar has ended, they aren't accessible anymore. You should have control over your own mute button at this point. I'll kind of go through and double check that everybody does. We just ask that it works a little bit better if everybody stays muted unless you are asking a question. For question asking, we find that it works best to use the chat function. We are also recording this, and the recording will be available, posted both on our website and emailed to you as one of the attendees at the conclusion of the webinar. And finally, along with the recording link, we will also be sending you a brief feedback survey, and we really appreciate if you could take the time to fill that out, and once we have received your response, you will get a certificate for your PD hours for attending this webinar. Okay, and with that, I'm going to hand over the reins to Richard, and he can begin his presentation.
All right, excellent. So welcome everybody. Today we're going to be talking about computational thinking in the math classroom. My name is Richard Bell. A little bit about me: I studied over at Drew University with a degree in applied mathematics. I was hired 14 years ago now to teach mostly math classes. Algebra II and geometry is what I started with, but I also taught web design classes. Only recently, I think within the last 6 years, I've been switched over to teaching mostly computer classes. I've been teaching the AP Comp Sci class, the CS Principles class. We started game theory. 4 years ago, I joined up with Keene University to teach their non-major intro to computer science class, and then since then I've moved over into the Java class. So I've been quite active in teaching, but honestly, I started out as that math teacher. That was my original goal, but we discovered something throughout the course of teaching, that students really weren't too.
Can you sit up?
Yes.
He doesn't know. Sit up.
Huh? Can you sit? Can you sit? Can you sit?
Sounds like I am.
All right. The students themselves have changed over the course of a bunch of years. Since I was in the classroom and we had to memorize things. So we had a formula, and we were given 100 problems, and we were to use that formula to solve those 100 problems. That rote memory is something that worked for us some time ago, but student retention has changed throughout the course of the years. Their attention is obviously elsewhere, between computers and cell phones and all kinds of different social media. The attention of the students definitely wanes when they're not stimulated by the content that we're trying to teach, or if the material itself is dry and mechanical. It's not enough that we just teach the particular concepts of math, but the practical uses need to be involved in order to keep the kids' attention, to really place why we're learning what we're learning. even with homework, the amount of homework that's given, or in cases like my schools, the homework that is copied instead of actually worked on, it just needs to be more meaningful and less about repetition and more about the actual meaning. So the trick then is to get these students to think about the problems that they're actually working on. Think about how to solve the problem instead of just memorizing the content that goes into it. That's where the idea of computational thinking comes in. Thinking about how to solve the problem instead of just memorizing the 3 steps that it takes, the 5 steps that it takes. The common phrase that goes along with computational thinking is algorithmic thinking. A lot of times those are interchangeable. But for the most part, though, the computers themselves are used to assist, not to do all the work for us, but to assist with some of to computate some of those things a little bit quicker, to generate a whole bunch of data that we can then use. But computers are used to assist instead of actually to do the work that we're actually looking at. But the computational thinking itself is really based on these 4 parts. Taking a larger problem and breaking it down into pieces, finding patterns and relating it to things that we've already done, that we've already known, and then solving those parts of the problem. The term there is called abstraction. It's a fun word that just basically means to solve the problem, solve the pieces of the problem and put those pieces back together to solve the larger problem. But then the idea is to create these algorithms, these list of steps that we follow in order to solve this entire problem. And a lot of times that uses a computer, but not really always. The computer is a useful tool. It's not, sometimes the computer is accessible. Back in the day when our teachers said that we never had a calculator in our pockets, so we had to learn to do the math on our own. That's not really around anymore. We have calculators in our pockets. We have tiny computers in our pockets. But not all of our cell phones or our mobile devices are actually useful for solving some of these larger problems. So we need to be able to think, or students need to be able to think through those problems and kind of act like those computers. But the big purpose is that algorithm that they're putting together in order to solve that problem. In doing so, in focusing on actually solving, thinking about the problem and solving it, helps put the ownership of the problem itself on, or the learning on the student. The understanding is not just being transferred from the teacher in the front of the room to the student. It's that ownership of it is more on the student. Sometimes in the educational world, those terms of problem-based learning or flipped classrooms are buzzwords that go along with it. They're useful. I don't know. I use problem-based learning in most of my classes just because it's allows the students to utilize, to grow and build on their computational thinking skills, to think about those problems before they actually just jump in and follow the same 3 steps to solve hundreds of problems. What's interesting about computational thinking, though, is you may already be doing this. It's putting a word or putting a phrase to some things that we're actually working on. In geometry, I know students' all-time favorite thing in geometry is proofs. But starting at a particular place and having to end at another place, setting up the patterns and the algorithm in order to get from point A to point B based on things that we have in the past, or things that we've known, things that we've put together, laws that we've put together that allow us to step from point A to point B. Those proofs are an indication of an algorithm that we have to put together in order to solve. In algebra, the factoring quadratics that was a challenge to do as a student, but then in order to recognize those patterns in order to quickly factor quadratics, that's something that's improved in my own personal skills after I had to teach that. Teaching Algebra II, 26 different sections of it over the course of my teaching career. Or even in algebra, this is something that I tried when I was teaching Algebra I. Instead of just teaching them slope and y-intercepts and then using linear regression models in order to find equations of lines, I did it backwards, using linear regression models. So we gathered up a whole bunch of data and then determined that all of our data was pointing in the direction of a line. Using that to teach slope and y-intercept is more interesting, and it's more pertinent to the kids' skills. It's something that will help them retain it a little bit more than just memorizing y equals mx plus b. So today what I wanted to show you guys were a couple of other projects that I've put together in both geometry and algebra to help build these computational thinking skills of my students. I have a couple of attachments that of the assignments. Feel free to use them, change them. I think I'm pretty good on spelling errors, but I don't know. Yeah, math teacher. The first example I have for you guys is in geometry. I taught this for quite a few years. We're doing interior and exterior angle measurements. We're talking about similar shapes, and then we were talking about scalars, increasing and decreasing size of objects and everything. Before you can get into this project, the basic shape vocabulary needs to be there. Pentagons and hexagons and octagons, the idea of interior and exterior angles, and then I did a little bit of basic coding, which I'm going to show you guys. The program that I'm using, this is called Build Your Own Blocks. It may look like Scratch, it may look like Snap, because that's where it came from. This is a version of those programs that I was able to download for free from Berkeley's Snap website. So here's their Snap website. The program is available online. It's called Snap, so you can do everything within browser. But I just happen to, for a few years, not have reliable internet. So I downloaded the program, and that's what this is. It's basically just, it's a blockly programming language. The blocks that we're using are motion, so we're moving and we're turning. And we are repeating that a bunch of times. And another thing is put the pen down when we start and pick it up when we're done. So the idea of this is I've already taught them a little bit about drawing a square. So the idea of a square with 4 sides, we can make it as big as we like. And then we know it's a 90-degree turn. So if we repeat that 4 times, then our object will draw that square. And that's what this block is, and this is something that we would have done. This would be like the first lesson, teach them about, the first part is pointing direction 90 degrees, that just points them to the right. Putting the pen down, repeating, and turning 90 degrees. This size is a parameter, and so we talked about being able to change that number from outside the block. The phrase that I talked about before was abstraction. That's the idea here that this block says draw a square. We wrote the code for drawing the square, and then we hit it inside of the block. So if I wanted to draw 2 squares, I can just tell my program to draw both of those squares. I can do it further. Oops. And so the same piece of code can draw squares of varying sizes, and the code inside there, how to draw a square, is now hidden, and then I can use that piece of code as many times as I want, or draw as many squares as I want. But then we talk about squares, and we also talk about triangles, and so here's where we start getting into exterior and interior angles. So turning north, let's see. Turning north, we're using our exterior angles because the angle is from the outside turning north. As our object is facing to the right, when he turns, he's going to turn this way. That's the counterclockwise turn. So that counterclockwise turn is the exterior of our shape. So it allows our object to going 120 degrees. That's the exterior angle of an equilateral triangle. Students then, without being told what that measurement is, might try something different, because I know that the interior angles of a triangle are 60 degrees. So if they try something different and it doesn't quite work out, the explanation there has to do with the exterior versus interior. It's a clockwise versus a counterclockwise turn. If we did 60 degrees clockwise, then our triangle would point south, and we would be turning the interior angle measurement. But since we're turning counterclockwise, it's the exterior angle measurement. So the students would be able to test out those particular values in order to find one that's going to actually work. Something basic like a triangle. So working together with the class on squares and triangles, we get the squares and triangles. Then the assignment then goes that the students are then to go further and make a pentagon, to make a hexagon, to make an octagon, to make a decagon, to even make circles, and drawing each of those. Anytime we do that, it's the number of degrees that we're turning is going to keep changing. If they're going to keep trying different values to see how that actually works, until they get a shape that the beginning and the end, those are going to touch. The intention there is to get it so they find that pattern. The pattern in any of our shapes, the pattern in all of our shapes about what are the interior angle measurements, what are the exterior angle measurements of a shape with any amount of size or any amount of sides, so that the intention is to end up with a block that looks like, draw a shape of blank sides, so that they can draw a shape of, and any number they put in here, then our character would then draw that shape with that many sides, whether it's a square, whether it's a pentagon. So then that's generalizing the formula for determining the interior angle measurement, or even the exterior angle measurement of a shape, based on whether you want the shape to point south, or to be created south of the object, or south of your sprite, or north of the sprite. The amount of coding that goes into this is not a heck of a lot. It's fairly straightforward, keeping to those 3 tabs: motion, control, and pen. There's plenty of other things in this program that work similar to that. In Snap, it's the same thing. There's motion, there's pen, and there's control. They're all the same type of blocks, but you don't have a fun character. That's just, his name's Alonzo, and that's an arrow, so it's not as much fun. But allowing the students to actually determine these particular values and build from that. The only thing that I actually give them is after doing the intro to picking up the pen, putting it down, repeating, moving, and turning, and I say, all right, we got to build these equilateral triangles, pentagons, hexagons, octagons, and then we can actually get into the putting together stars, which is a little more challenging, because then that gets more into the number of rotations that our character is going to go. As he turns all the way around in a regular shape, he's going around once. So he turns all the way around 360 degrees once. But then in a star, then it builds their spatial reasoning to determine how many times a sprite would actually have to turn around in order to make a star. with 5 points, or a star with 8 points or 10 points. And in those, they're actually experimenting with the different number of rotations and the different angle measurements, and they could actually come up with some pretty interesting looking stars. But that's an extension on this one, that building the shapes that I like to throw in there for some of the students that really understand this, and then some of the students that struggle, but I threw that in as an extra thing. The other piece that this whole thing works out to is putting together something like building a house. And so taking that piece, the idea of the house with the top, and then we build in the windows and a door, solving each of those pieces separately, and then putting them all together would allow you to and then putting those solutions together in order to build a house, and allows us to build a house. So then here's my block I've created a layer of abstraction. So building a house, all the code is inside there, and the code inside there is drawing squares and triangles, and inside the square there's the code for that. But then each of those pieces are solved individually so that I can put them all together to solve the larger problem of actually building a house. So then those ideas, I'm looking for, in my case, I was looking for all of those pieces. So did I share? The rubric then is checking to see that they're able to create these shapes. I think I put septagon in there too, because they were curious, because we did 5, 6, 8. They wanted to do 7-sided figures. So I put that one in there in the rubric. Checking off if they actually wanted to, if they created it, then talking about what the interior, exterior angle measurements actually are, and then putting together the patterns to find an n-sided figure. There's another piece on this one. The spatial thinking about these sprites is a little bit difficult for some of the students, because they're sitting at a computer looking at a flat screen, and when it says turn to the left, turn to the right, they have trouble seeing that. So because they're not facing in the same direction as the actual sprite. So what I have for this assignment, what I have on the floor are two masking tape shapes on the floor. One was a square and one was a 5-pointed star, so that they could pay attention to which direction they were turning. So they walked along that square. Okay, I'm turning to the right, it's doing this. Or in that star, how many times am I spinning around? So how many degrees is that? In order to figure out how many times how many degrees I need to turn for each of those points of the star. Or I had the square. I think one year I had the triangle instead, because we were talking about the exterior turning clockwise versus counterclockwise. But sometimes that spatial reasoning needs to be enhanced a little bit more, just because they have trouble seeing which way little Alonzo is actually facing. Well, it says right here, his arrow is pointing to the right. Yep. So that's my throwing things, or not throwing things, this is my geometry drawing shapes project that I used. I had freshmen and sophomores in the class that I was using this project in, and it seemed to go pretty well. Some of them actually I convinced to take computer science, because we used this program, the intro to computer science class, because they liked the program. They liked using it to draw all kinds of different shapes. I thought this was a good way to show interior, exterior angle measurements. Let's see. The other project, this one's probably my favorite of all in Algebra II. I taught this class from the beginning of teaching to I think about 5 years ago, I probably taught about 26 sections of it during that time. And some of the things got a little tedious after all that time, just because I was teaching the same thing over and over again 4 or 5 times a day. So I created this project for quadratics, also because I know how to juggle. So that sometimes helps in the description of this project. The idea of this whole thing is we are modeling the equation of a ball in flight as it goes up, comes back down, and we get to throw things across the room. So kids in groups of 3 are throwing a ball. Usually I have tennis balls. I have a set of juggling balls. There was a ping pong ball, a bouncy ball. I think those are the ones that I had. One of those Nerf squishy balls. But before this, we did this whole thing. The section before this, we did systems of equations, but with 3 or more variables. And we've done the basics of quadratics. So we've talked about the equation. We've talked about vertices and y-intercepts, and the basic idea that you need 2 points to find the equation of a line. We need 3 points to find the equation of a quadratic. And so we give them, I give them 2 stopwatches and a measuring tape to use to plot height over time. As they throw a ball from one side of the room to the other, students stand various distances away so that they can get different heights. And it was interesting to see over the years, some of these students have never used the measuring tape. They've never used stopwatches. They had a lot of trouble trying to figure out if they threw the ball from their waist, how high their waist is from the ground. So it was an interesting element to add that piece in there. But the idea of this throwing things assignment, it's this one. That's the only thing I'm really giving them. They need to figure out 3 points on the ball's flight, then they're going to use their algebra skills to figure out the equation of a quadratic. So I drew this up. So here's what's actually happening. The students are going to be measuring where they threw the ball from, time and height. Somewhere in the middle, time and height. And then somewhere at the end, their third partner, time and height. And so from those 3 points, they got to find this equation based on the x and y values that are in there. Basically, the idea is taking this equation 3 times, substituting these values in, and so you have a system of equation with 3 variables, or technically, if you use this value, 2 variables. So you can solve this system of equations. Students spent plenty of time using the graphing method, the substitution method, the elimination method in order to solve systems of equations. What they ended up using for this one, because they didn't necessarily realize that that first value is the y-intercept, it is the value c. They were actually using matrices in order to solve. So we had graphing calculators in the classroom, so they would set up the coefficients of the equation, put it into a 3x4 matrix, and then use the feature in matrices on row reducing into echelon form in order to solve for A, B, and C. The other way to do that is just calculate it based on using one of those other methods, elimination or graphing in 3 dimensions probably wouldn't work without a computer. I can't draw in 3D. But then the idea is just solving that system of equations to find the values of A, B, and C. And then from that equation, then you find the maximum height of the ball in flight, when it's going to hit the ground if it's not caught. And actually, this ends up having a positive value and a negative value, so interpreting what those values actually mean. And then comparing your height versus the ball, or your height as far as you can reach up in the air, if you can actually reach that. Our rooms are, I believe, 12 feet high, and so the kids could get anywhere from, and some kids would throw it really low, some kids would throw it really high. Most of the time they would throw it pretty high, but then doing those evaluations, how high was the ball after a second, 2/3 of its maximum height. And then some of us, this was an external one. They went outside. Only if you do this in nice temperature. This was chapter 5, so this was the winter. So we actually had to go to the gym for this. But they were doubling the time, so they wanted to determine, this is now into physics, whether moving twice the distance away or throwing it twice as high would actually double the time. And so then they are testing their hypotheses on this. But utilizing the calculator or computer in order to solve this equation is a big part of this. But for the most part, the only information I really gave them was the equation of the quadratic, and they need 3 points. I just kept reminding them that those 3 points were x and y, solving height over time. So just that bit of information, then they had to break down the problem, figure out from those 3 pieces, solving this, and then using that to solve all the other ones. That was something that I really enjoyed doing in class. First off, because then you're just throwing things around the room. And that's always interesting to students to pull it out of the let's sit here and just talk about the quadratic formula or the equations to find the vertex or x-intercepts and everything. Well, x-intercepts is the quadratic formula. But instead of just sitting there and doing those things rote like I did when I was in high school, we tried to put meaning to all of those things by throwing a ball across the room. And while I'm describing this whole thing, I tend to juggle just because I can, and it's also demonstrating each time I throw a ball up in the air, it's going up and it's coming back down. So technically, I wouldn't have to throw it from one person to another, but getting all 3 people involved is a useful thing there too. That's my throwing things assignment. Yeah. A big part of that, though, is that the students are developing the plan. They're not really given too many directions beyond the 3 points that they need. 3 points on a quadratic to determine the function, and they're doing the time as the independent variable and distance is the dependent variable. But besides that, that's the only instructions they're getting. But these are 2 examples that I've used in my classroom. I know I mentioned some other ones, the proofs that we do in geometry, the linear regression models. I mean, this one could also be a quadratic regression model, but normally we haven't done that at this point. So we end up using things that we've already known. So establishing that pattern from something that we already know, solving systems of equations that have 3 variables. Yeah. Well, those are my 2 examples. In math, you find computational thinking a lot. Stats is in there a heck of a lot. I was a sociology teacher, and she reminded me about this. The data sets that they use from various surveys to identify those trends. She's constantly pointing out to people the flaw in the way that our perception of how our society actually feels. She does it in her school all the time, but she uses Google Forms as a really easy way. Some schools have Google accounts and everything, but it's a super easy way to acquire that data, and then they organize it and graph it and everything for you. But that can also be used in your stats classes in order to analyze those things, in order to interpret all that information. In science, this is an interesting one that we tried to do back when I first started teaching the AP Computer Science class. There was the case study on Grid World, and it allowed us to create these objects that would run around in the grid, and they would interact with one another. These simulations that can be put together utilizing that Grid World, or as John, if you're here, your suggestions here on rabbits and wolves. These simulations allow us to study the behavior of animals and pretty much anything over a course of a bunch of different steps. Here's our, let's see, we've got rabbits, and we've got wolves. The wolves will eat the rabbits, but then the rabbits will try and find each other and eat the grass. Everything's green is grass. It allows us to see how these would react in the real world without actually having to go out there and study them. It allows us to go through lots of different steps of generations of rabbits where they would not easily be studied out in the real world, but these simulations then can model that behavior, how the rabbits are multiplying and eating all the grass, and how the wolves are actually eating the rabbits. And it allows you to check out population graphs, so you can see how loss of the grass would actually, and the leaves and everything, would decrease the population of rabbits because they had nothing to eat, so they would end up dying. And how the increase of wolves would actually affect the population of rabbits, as well as how much grass is actually there. So as the wolves increase, if there are no rabbits to eat the wolves, or rabbits to eat the grass, grass will keep increasing. But as long as the rabbits aren't there, wolves will keep dying. So in the end, we'll just have grass. If I go faster, we just have grass. The great thing about these simulations are there's plenty of them that exist that you can utilize to change things around. This one has some other activities. Checking out some other ones on life, but the idea is, and these already exist, and so you can actually check out how they interact. Or my suggestion when we were working with that grid world case study, I had my class work with the environmental science class to create predator-prey relations, or symbiotic relations, or what are the other ones? Parasitic relations. And so then they would create these objects, and then they would interact with one another, and we'd toss a bunch of them out on a screen, and we'd see how they would actually interact with one another. This one's called the game of life, where each of those squares either light up or go dark based on what's around them. Here are the particular rules for this one. And so each step, these guys are lighting up or darkening based on the number of things that are around them. But yeah, it's an interesting activity. So you can look at different patterns and see how they are, how they build and grow, and then they sit at a particular color, they sit at a particular shape, or they disappear entirely. Point two. But it's an interesting way to see the different shapes that will run across the screen, or the ones that will stay in the same place, or the ones that just keep rotating back and forth. Anyway, but yeah, these simulations wouldn't be able to be created without the use of these computers. The steps that go into them, all the details that are programmed in there, wouldn't be useful without, or wouldn't be created without computers. But then they would use those ideas in order to study those environments and check out those simulations. The other thing that actually I was doing, setting up for this presentation, was preparing and writing these research papers, putting together these outlines of all the information that you're going to be talking about, all the information you can include in one of these research papers. It is an exercise in computational thinking, breaking down the big problem of writing this paper, or conveying a point, and breaking it down into pieces, and working on that introduction, and researching those main points that you want to make, and then putting them all together in your final product. That is, it's a computational idea. Whether or not you're using a computer is it's not necessary, but most research papers are typed on a computer, at least. But then there's an interesting lesson that I found on finding patterns in misspelled words. I got a link to it. It's online. It's a Google Doc that someone has shared. But there's some interesting stuff on here, and it takes a little bit of work in terms of they're using Google's Google spreadsheet in order to see how computers are finding mistakes in spelling of words, maybe not based on whether or not it actually knows how to spell the word, but how other people are actually looking for that word, and then basing its assumptions and everything on that word. But it gets in a little bit in-depth pieces on the spreadsheets, so this is kind of an upper level thing, but I thought it was interesting, finding patterns in spelling history, or yeah, spelling and history. So computational thinking is not just localized in mathematics, even though a lot of our topics in mathematics can be boiled down to these computational thinking ideas. It's also in all of our in a bunch of our other subjects as well. But it also helps out with that question that we get quite frequently in just about any class that we're teaching. When are we going to need this stuff in the future? It's apparent that a lot of times we might not need to know how to draw a linear inequality. That will probably never come up in life after what is that, Algebra 1, but utilizing that idea and then putting it into a computer to see how a drawing, a shape, a logo for a company is created using this equation, so that we can put it on a business card, on a letterhead, on a billboard, on a website, and that equation will make that shape look the same on all of those things, and not be pixelated and not being like that. Using those equations in order to create those shapes allows us to scale those images as best we can, or scale them so that they look the same no matter what size. But I mean, this computational thinking helps answer that question. So it might not just be about that topic that the kids are learning about. It might be about the whole idea of just learning how to solve a problem that at first might be daunting, and then breaking it down into smaller pieces. That idea, that ability, that skill to actually do that is what's the piece that we're actually trying to teach. Content itself, sometimes they might not need that past the massive amounts of standardized tests that we have to do. But yeah, so sometimes that computational thinking is the answer to when we'll need this in the future. Yeah, so I'm pretty close to being done. Is there any questions? Does anybody have any questions? You guys can feel free to unmute yourself, or if you want to send something through the chat. Anything at all. I've attached, well, Lynn's attached the documents that I had, the turtle drawing or the throwing things. We've attached those documents, so if you guys want to check those out, you're more than welcome. I do have, at the end of this presentation, there's a bunch of links to a couple of articles on computational thinking about teacher education, computational thinking. One's talking about cheating, and the Wolfram Alpha website. Another one is on the difference between coding and computational thinking. But for the most part, I mean, the ideas that we're trying to get across are logic, trying to go with a systematic approach to solve those problems. So if the problem is something that they haven't seen before, it's a systematic approach to break it down into problems they have, or something that they can find some sort of pattern. Because being able to spot that pattern in a topic and relate it to a past problem is part of most of what this is really all about. Those problem-solving skills that this entails is usually on just about every job description as an important skill that people should have. And it really covers lots of professions on all different levels. we're preparing our students for their futures. So it's not just the job that they're trying to get, but it's also just in life in general. They need to be able to think for themselves. They need to be able to accurately and effectively solve their problem, as opposed to just using somebody else's idea and trying to do the first thing they run to is Google and try and find somebody else who's already solved it. But being able to solve the problem on their own is a better skill that this is trying to enforce. And the last one is computer skills, because computational thinking a lot of times uses computers, but it's not always necessary. The people who utilize these computational thinking skills don't need to be coders. They don't need to be programmers. Not everyone's going to be a computer scientist. That's not a skill. That's not a trait for everybody. But there are certain skill sets that everyone can have, that everyone can possess, and the computational skill set is one that can help in just about all aspects of life. But you know, a little bit of computer skills certainly won't hurt. Cool. If there's anything else, any other questions? Or any questions at all? Cool. Here are my resources. I forgot this one. Google has a free computational thinking course for educators. I actually just, during the process of putting stuff together for this presentation, I just found it. So I'm probably going to go take a look at that and see what it's actually all about. But it's something interesting, and I believe it is free. So that's always a useful thing, if that works. Free online course helping educators integrate computational thinking, math, humanities, science, and computers. So that's another link that I would suggest. Here's Snap. That's Berkeley's version of the BYOB program that I was showing you. Scratch is another one that's the same thing. And there's a couple articles. The last thing, this is one that I mentioned, the sociology aspect that my wife has been working on. She's gotten into these other further data analysis tools, the SPSS and GIS. They're huge contributors to a lot of the decisions that are made in most every business. They analyze all kinds of data fairly quickly that helps them make decisions about where to advertise, how to advertise, where to move products, where to do anything really. Most decisions are used, and so stuff like using Google Forms and getting into stats will then build into these two programs. I left links to their Wikipedia sites just so you see what they are. But yeah, that's statistics, and that'd be a good one to get into. Cool. I think that about wraps it up, Lynn.
Okay, well, thank you very much, Richard, for presenting for us this afternoon. I'll open one more chance for questions. Anyone have any last questions for Rich? Okay, well, I thank you all for attending. And just a quick reminder, I will be sending out an email probably tomorrow with a link to the video from this in case anyone wanted to review anything that Rich presented, as well as a link to a post-webinar survey. And if you wouldn't mind taking a few minutes to answer that, then I can send out PD certificates once I get your response. Again, we do have other PD opportunities, all of which are free, and we will be posting our new full lineup with workshops and webinars alike probably in the next couple of weeks, so you can look forward to that. So again, if there aren't any last questions, which I don't...
Lynn, I see Sue's hand is up.
There we go. Okay, so yeah, I saw Sue's hand. Sue, do you have a question? You can either unmute yourself.
I was just going to say thank you. That's all. No question. Thank you.
Okay, I appreciate it. Okay, well then if there are no other questions, I thank you all for attending, and thank you again to Rich for presenting this afternoon, and enjoy the rest of your beautiful afternoon. Good night.
All right, take care.